Hello everyone, I hope you're doing well. In this video, we'll be finding out the energy to the second excited state in 1D harmonic oscillator by using the variational method or principle. So before that video, we have already calculated the energy to the ground state as well as to the first excited state of 1D harmonic oscillator using the similar method, that is variational method. And now we are doing it for the second excited state. So let's quickly get started with our method. And as I told you people earlier in the video that I did for the conceptual understanding of variational method, it is that determination of higher states depends upon the lower states, okay, the consecutive lower states. For example, here we want to calculate the energy for the second excited state, so we should know what the first and the ground state looked like. Okay, the wave function, not the energy. We are not concerned with what was the energy for the first excited state and ground state while solving the problem, but we are concerned with what was the wave function for the first excited state and the ground state. Okay, so these are the first things that you should know, and then these things will help you to form the basis of your solution. All right, because in variational method, I have told you people, the first step, the first crucial step that defines the whole solution is to devise a trial wave function for the state whose energy you want to calculate. So it's second excited state in this problem. So devise a trial wave function for second excited state. And to devise a trial wave function for the second excited state, we would need help from the knowledge of first excited state, wave function, its wave function actually, and the ground state. And there is no state other than that, lower to second state. So these are the only two states, and they will help us to devise a perfect trial wave function for the second excited state. That is why I told you people that before proceeding with the solution, you should think about the lower states, okay, and then proceed with the solution. Now let's see what we can do here to devise a good trial wave function. What we can do here, that what was the ground state and what was the first excited state, and according to these states we'll devise the wave function for the second excited state. So in ground state, we said that in ground state the wave function should be even, okay, and in first excited state the wave function was odd. Hence the second excited state will have a even function, or it will be a even wave function. Okay, so we will write the key things here. This is all that we are doing in rough work. What you will write in a neat form in your paper, I write it down later on when I make it clear to you that how we devise that trial wave function. This is all that I'm doing it for, making you people understand that how we can devise a trial wave function. And I write all of these things in neat form that you can use as notes or write on exam or whatever like that. Okay, so the key things, the first thing is that it should be an even wave function, because the first was even, the second is odd, the third will be even. And we do it in order to ensure that the wave function is orthogonal. Okay, so what about the second thing is nodes, number of nodes. Ground state has 0 nodes. First excited state had 1 node. So second excited state should have 2 nodes. Nodes means the points where the wave function becomes 0. So there should be 2 points where the wave function becomes 0 for the second excited state. So we will write 2 nodes. Okay, and there will be same exponential factor in here just like before, to ensure the wave function is defined at infinity. so that it's a well-behaved wave function. All right, so there will be introduction of one other adjustable parameter. We'll have alpha and beta as two adjustable parameters involved in here. I'll give you the reason after writing down the trial wave function, okay? Because I can't make people understand at that point, but after devising that trial wave function, we can do this. So psi 2 x alpha and beta, there will be two adjustable parameters. We'll see in here. We'll have a normalization constant as always, because normalization constant is always there, whether it's ground state, first excited state, second excited state, or whatever state it is. The normalization constant is always there, so let the normalization constant be capital C. Okay, then as usual we'll have this exponential factor. Now we should have a even wave function, and even wave function normally comes in with even powers, so we'll have an even power, and it should have two nodes. And for that purpose, what we'll do here, in previous case, in first excited state, we just multiplied x with e to the power minus alpha x squared because we wanted one node, so this thing ensures that. But here we want two nodes, so what we do here is that we'll subtract it by 1 and we'll multiply it with adjustable parameter, okay, beta in here, and that's the case, and we'll multiply this thing with the exponential factor. Okay, in case of wherever it's x, you have to introduce the adjustable parameter wherever it's x. In case of psi 1, what happened here, a is normalization constant. If we introduce an adjustable parameter with this x, wherever there is x, you have to introduce an adjustable parameter. That's the rule that I have shared in here. So why we didn't do that in case of first excited state, if you watch that video, then you can relate to it. If we multiply a adjustable parameter in here, let's say it's beta in here, then beta in a is a constant, and it could be written as a single constant. Let's say it's d, which is another constant, because beta is a constant, adjustable parameter is actually a constant, a is a constant, so we can combine them into a 1. So there was not a need to add any other adjustable parameter which is being multiplied by another constant, so it makes a single constant. But here the case is different. It's beta x squared minus 1. It's a whole different factor, so we have to introduce a different parameter here. We see in here, okay, so wherever there is x, you have to introduce a adjustable parameter as long as there is not any other constant in which it could be integrated. In case of beta x squared minus 1, you can see that the normalization constant is separated from this adjustable parameter, so it holds its own identity in this equation. Okay, and you will see later on that there will be two different conditions that this wave function will go through. The first would be the orthogonality condition, the need to satisfy the orthogonality condition, and the second one is the variational principle, the need to satisfy the variational principle. So there are two needs in here. Okay, but the main thing that determines the presence of adjustable parameter is x. Wherever there is x, you have to have an adjustable parameter multiplied to that x factor. All right, so that's the rule and you have to follow it. There will be several things that would be different in this case, and they were not present in the ground state and the first excited state. This case is a bit more complex, you can say, or detailed, requires more things to be determined than the first and the ground states, and that is one of the reasons that we mentioned in the limitations of the variational method, that as we go to the higher states, the method becomes complicated. Okay, and there will be several adjustable parameters, there will be several unknowns and conditions to be satisfied before we get into the desired result of the energy for the excited state that we are wishing to calculate. So I hope you are convinced enough about this wave function. This is a trial wave function that we'll be using here, and psi naught was quite simple. Psi 1 was more complicated than psi naught, and psi 2 is even more complicated. As you can see, not much, it's not that difficult. You will see the mathematics and integration would be more or less the same but lengthy. And yeah, this is all we shared here, and I hope you people understand that how the knowledge of previous states helped us to devise a good trial wave function for the second excited state. Okay, that was all we needed to know about it. But in case of orthogonality condition, we need to have a knowledge about the ground state wave function, exact knowledge about like what it was exactly equals to. Okay, so that would be needed later on, you'll see it. And I'll be talking about the orthogonality condition in detail when we'll be calculating it. Okay, so let's write all of these things in neat form so that you people can make notes and you may know that what to write in exam when this problem comes in, because it's a really important problem. So let's do that. I hope you got it so far. The ground state, we'll first talk about the previous state and the first excited states of 1D harmonic oscillator has the following form. Okay, we'll write the trial wave functions because they contain the essence of the wave function for the ground and the excited state. But later on, we would need the ground state wave function exact. Okay, so I'm writing here the trial wave function only because we don't need that much detail. So that is the ground wave function, while, oh sorry, it's psi 0 and psi 1, that is equals to b x e to the power minus beta x squared, let's say. Okay, so these are the ground and the first excited state wave functions for the 1D harmonic oscillator. Now let's devise a trial wave function for the second excited state of 1D harmonic oscillator. Since, let's talk about the even and odd nature of the wave function. Since the ground state wave function had a even wave function, was an even wave function, and had 0 nodes, while the first excited state had a odd wave function with 1 node. Hence, the second excited state should have a even wave function. Okay, even, odd, and then even, so it's even wave function and 2 nodes. To satisfy the orthogonality condition, And other unknown facts about the second excited state wave function: two adjustable parameters would be introduced. The trial wave function is hence given by psi 2, which is a function of x, alpha, beta. C is normalization constant, beta x squared minus 1 into e to the power minus alpha x squared. Okay, you could have subtracted 2 here, 3 here, 4 here, or whatever number, but we made it as simple as possible, so we took 1 because it's simple. We could have used 2, 3, or whatever. We were just concerned with the factor that it should make 2 nodes. Okay, so I'll justify it that how it makes 2 nodes and all of these things. It will be a short description. So this is the trial wave function. Let us call it as equation number 1. Okay, or this is 1. And now this now C is the normalization constant. A well-behaved wave function should satisfy the normalization condition and orthogonality condition. These conditions will be used later on in the solution as well. That is why it's worth mentioning and we should mention it. So let's mention the normalization condition first. We'll do the heading and then we'll write the normalization condition, which is the scalar product with itself. So we are talking about the second excited state, so it's psi 2. Its scalar product with itself should be equals to 1. That is the normalization condition. Okay, the scalar product, the self product should be equals to 1. This is a normalization condition. And then let's write the orthogonality condition. Normalization condition is for similar wave functions. Orthogonality condition is for different wave functions. And we'll consider for psi naught, psi 1 and psi 2, since these are all the wave function lower to psi 2. So here we'll have the same wave function. Okay, since there are two different, so there will be two different orthogonality conditions. Possible orthogonality condition with psi 2. Psi 2 is the main character. Okay, so it will be similar in both cases. Here it will be psi naught and here it will be psi 1. And it should be equals to 0. This is orthogonality condition. Okay, and let me mention here that in rough work, or you can write in here, since psi 1 was a odd function, wave function. Let's write wave function because otherwise it will be offended. Psi 1 would be offended that I'm a wave function, I'm not a simple function. So it's a wave function, and psi 2 is even wave function. So the product, as we know, the product of even and odd wave function, our whole space, which is what these scalar products mean, wave function, our whole space is always 0. So it means that this condition is already satisfied. Psi1 and psi2 scalar product would be 0. It is because psi1 is an odd function, wave function, and psi2 is an even wave function. In a product of even and odd wave function, our whole space means from limit minus infinity to plus infinity, this integration is always 0. You can even search about it if you don't trust me. Please trust me. It's true. It's always true that the integration of a even and odd function, okay, when they are being multiplied with each other, the product of even and odd function, and if it's integrated between the similar limits, it could be minus infinity to infinity, it could be minus 3 to 3, it could be minus 4 to 4, but whenever there are symmetric limits like that, okay, similar limits but from negative to positive but the magnitude is same, the integration is always 0. Okay, but here what we can see here that but psi naught is even wave function and psi 2 is also even, hence we have to make it orthogonal. Okay, so we'll find a condition that will ensure that the final psi 2 is orthogonal to psi naught. Okay, so hence we have to ensure that psi 2 is orthogonal to psi naught. Let's do that first. Okay, and then we'll calculate the normalization constant from this normalization condition. Okay, totally up to you if you want to calculate normalization constant first and then this or then this. It's totally optional. They are both giving us the conditions and the value of some constants, so they could be done interchangeably. There is no issue at all. So I'm doing it. I'm calculating the orthogonality condition first because we have already opened up the discussion, so we'll lead it towards the condition that ensures that psi naught and psi 2 are orthogonal to each other. So here we can see that we have this condition psi naught is equals to 0. Okay, for that purpose we should know what exactly psi naught is equals to. Okay, that is what I was talking about. Here psi 2 is the trial wave function, the one, this one. Okay, while psi naught is actually the original wave function that we calculated before. So let me mention the where psi naught equals, let me see, it was somewhat m omega by, yes, it's m omega by pi h cut to the power 1 by 4 e to the power minus m omega by 2h cut x square. Okay, simple is that. It's really simple. It's m omega by h cut with pi in denominator, m omega by h cut with 2 in denominator. Just a slight difference. It's really easy to remember. So this is psi naught and psi 2 was c beta x squared minus 1 e to the power minus alpha x squared. Okay, so let's write it. Let's write this orthogonality condition in terms of, hence in terms of integration, we can write it like that. It's minus infinity to plus infinity, psi naught first and psi 2 static since it's in bra vector, but as we know that they are real quantities, they are real functions, real wave functions, so that is why they are just same, and they are 1D cases, so it's integration over x only, y and z doesn't matter. Let's put the values in here, and we have psi naught, this m omega by pi h cut power 1 by 4 e to the power minus m omega by 2h cut x squared multiplied by c beta x squared minus 1 e to the power minus alpha x squared dx. Okay, and that is all equals to 0. Remember that. So now the first thing that we can do here is to take these constants outside of this integral, and then we'll see what else we can do, because it will make the path clear. Okay, so we need to take the constants outside. So it's a bracket m omega by pi h squared power 1 by 4. Then we have c here, integration e to the power minus m omega by 2h squared bracket x squared. Then we have e to the power minus alpha x squared. Then we have beta x squared minus 1 dx. Now let's, since the bases are same, it's e base and it's e base, so the powers will be added. And one more notable thing here is that both of them have x square as variable power, so that's a plus thing. We'll add both these powers together, x square minus alpha x square. Then we have beta x square minus 1. We'll simplify this power, then we'll multiply it inside of this quantity, so that we'll have a simplified form and separated integrals to solve. We can take x square common, so we'll left with m omega by 2h squared plus alpha. Okay, and we have beta x square minus 1 as a factor being multiplied by this exponential factor. Now the next step is to multiply this whole integral inside, so the integration will be separated over both values, and I'm using the bigger bracket now, and we'll have this integration, this exponential factor, then beta x square. I'll write dx with it, because wherever there is integration there is accompanied dx, then minus sign, and this factor when multiplies with 1 brings back to be same, unchanged. So we have this quantity and dx over here, and the bracket will close. We can see here that we have now two integrations to solve. Solving this integration will give us the final result, or will make us closer to the result, because it's almost done. You can see how simplification, proper simplification, leads to simpler forms. So here beta could be taken out. I'm taking beta outside, so that we have a simplified integral. It's x square. I'm writing x square first, then exponential factor with m omega by 2h squared plus alpha first, then x squared in power dx. The negative sign, we have minus infinity to plus infinity, e to the power minus, I'm writing the constants first, then variable dx. So here we can see we have two integrals here whose value needs to be inserted into this expression in order to get what was there. It's psi naught psi 2, and that was equals to 0, you must remember. We can even do that after all these lengthy mathematics. So let's see what these two integrals equals to. And if you remember from the previous videos that we have learned integration formula that can generate several integrations results, several results for integration. So let's recall to that formula again. That formula was used for every derivation, like for the ground state, first excited state, and now in second excited state as well. So it's a really important formula. You should remember those important integration formulas which frequently appear in mathematical derivations. And sometimes what happens is that your tutor or teacher mentions these important formulas that are potentially used in those derivations in exams, so that's a plus point. But you can remember it as well, because we are doing it so many times that even I have remembered that formula. Let's write the formula. We know that this integration minus infinity to plus infinity x to the power 2n, which means there are even powers only. It is true for even powers of x, not for the odd power of x. So for odd powers there will be different formula, and we can see every formula that we are encountering here has even powers, like x squared, x4, x0. 0 is a even number, so x6, something like that. So it applies here. E to the power minus, I'm using beta x squared dx. Okay, anything that comes with x square power, any constant, is called as beta. Okay, so that on comparison we'll see what appears with the variable power in here, and we'll put that value wherever there is beta in here. Okay, so it's pi by beta 1 dot 3 dot 5 dot, and this multiplication carries on, and the last number to multiply is 2n minus 1 divided by 2 beta power n. Okay, so that is the formula with beta as constant in here. Okay, and in previous cases what happened was, we had 2 beta form here, so wherever there is beta you can write 2 beta and you'll get the same form. It depends what kind of form you have, so that is the most general form. Okay, and you can do it and get your desired result out of it by suitable modifications. So we can see here that we have two integrals in here. We can see here, this is the first one and this is the second one. If we talk about this first one, we can see it's x to the power 2. So we can compare the powers. I'm doing it in rough work to make you people understand. So here the power is 2n, and the one that we need is 2, so we can find the value of n that is needed. So n should be 1 to make it equal and just like the one that we need. Okay, so n will be taken as 1, and beta is actually m omega by 2 h cut plus alpha. You can use a different symbol here, gamma or something like that. It is not this beta. Okay, it is not this beta, it is just random name that I have gave here. You can use gamma or sigma or any other name if you are getting confused. So this is not that beta, this is not adjustable parameter. And beta we can see here is m omega by 2 h cut plus alpha. Okay, so we can get the value, which means that x to the power 2 e to the power minus, we'll put the value of beta, which is m omega by 2 h cut plus alpha x square dx. Now let's put the values in this side as well. So I'm gonna put it here because maybe it could get lengthy. So it's under root pi by beta. What is beta? It's m omega by 2 h cut plus alpha. Okay, and dot, then we have this term. Now this term decides the last term of this product. Okay, so let's put the value of n in here to see what the last digit would be. So 2 into n, which is 1 minus 1, 2 ones are 2 minus 1, 2 minus 1 is equals to 1. So 1 is the last digit, and we can see 1 is the first digit as well, so we'll multiply 1 only. Okay, and if we would have got 3, then we would have multiplied 1.3. If we would have got 5 as last digit through this number, so we would have multiplied 1.3.5. This number tells you that what is the last digit to multiply. So you'll continue from the initial odd numbers, and we'll terminate this product at this point, which we get in accordance to the value of n. So we have 2 beta, 2 into beta, which is 2 into m omega by 2 h cut plus alpha, and it has a whole power n. N is 1 here. Let's simplify. It's pi by m omega by 2 h cut plus alpha. We'll write it as it is, 1 divided by, we'll multiply 2 inside, and its whole power 1 doesn't matter. So it's, when we'll multiply 2 inside, so it's 2 in here and 2 in here. This 2 into cancels out, and it's m omega by h cut plus 2 alpha. Okay, so this is the value of the first integral that we have in here. Okay, now let's find out the value of this integral. We can see there is no x involved in here. It means that n is equals to 0, which means that n is equals to 0 is taken, And when n is 0, it means all of the terms in this formula where n involves will not appear in the result. So what happens here when n is equals to 0, these two terms will not appear and only this term will appear, and the integral is actually equals to this term only. Okay, so let's write it down because there is no n dependence anymore. So it's x to the power 0 e to the power minus beta x square dx equals under root pi by beta. That's the result. Let's write it in terms of the actual values that we have, and we can see here that here the beta is same. Beta is actually the constant that is being multiplied by x, so it's the same. So we'll write m omega by 2h cut plus alpha x square dx equals pi by beta, which is pi by m omega by 2h cut plus alpha. Okay, that is its value. Now let's insert these two values right back into this expression and see what we are gonna get. So it's psi naught psi 2 c m omega by pi h cut to the power 1 by 4 and beta dot. Okay, this is beta, and I am warning you, if you if you any of you is confusing beta with this beta, please don't do that. Please don't do that. It's the adjustable parameter, and that was a dummy value, just a dummy value. You can use a different one. That was my mistake. I should have used a different dummy value to represent it, but okay. So let's do that now. Its value is evaluated. Let's put it beta into this expression, which is pi by m omega by 2h cut plus alpha. Okay, 1 over m omega by h cut plus 2 alpha, then minus sign, then we have this term pi by m omega by 2h cut plus alpha, and that is it. And all of these things are equals to 0. Okay, now you can see, now we can eradicate this side. I'm not writing this side anymore. In next step, what I'm going to do is to write this side equals to 0. Okay, as you can see that I have written this form, and I have not continued writing this because it's not needed anymore, and we are just gonna get the relation that we were looking for. And we can see that this factor is being multiplied by this factor. We can take it's multiplied by this factor, it will be divided onto the other side, and it will become 0 because 0 divided by any constant or factor or variable or anything is 0. So this factor just gets to the other side and becomes 0, and it's beta, and we are left with beta. And what else we can take common is this whole factor as well, pi by m omega by 2h cut plus alpha. If I take it common, it's beta by m omega by h cut plus 2 alpha minus 1 equals to 0. I'll take it to the other side as well, and it will be eradicated from this equation. I hope you are getting it by how I'm doing it. It's just like m omega by h cut plus 2 alpha minus 1, and it's 0 divided by pi by m omega by 2h cut plus alpha. Okay, 0 divided by any quantity is 0, so we are left with 0. Okay, that is how we are doing it, and we are left with this quantity. Now I'm using every bit of my page because there is a thing that is called as sustainable use of resources, and we as consumers are responsible and have the responsibility to make the most out of the resources. Okay, don't waste them. And yeah, because if you are wasting them, then you are taking a whole part and contribution towards degrading the environment, and we shouldn't be doing that. Okay, so it's just not that we can't afford it, it's just like we should have that responsibility that we shouldn't be doing that. Okay, so we are left with, I am planning to use even this space, beta over m omega by h cut plus 2 alpha. Yeah, plus 2 alpha minus 1 equals 0. Since it's being subtracted in here, it will be added to the other side will become positive 1 onto the other side, and we have got our relation. Okay, it's being divided here, it will be multiplied in here, so it's m omega by a square plus 2 alpha beta equals m omega by a square plus 2 alpha. That was the relation that will ensure that psi 2 and psi naught are orthogonal to each other, while we have seen that psi 2 and psi 1 were already orthogonal. There was not needed any additional condition, but psi 2 and psi naught required an additional condition for them to be orthogonal, and this condition will ensure that they both are orthogonal to each other. Okay, so this we can call it as equation number 2. You must be following up the number, and as you can see, the background is changed and the day is changed as well. Since these videos are so lengthy, they take a lot of time for me to make, because I can't make them in one shot, and I have multiple tasks in a day, so I have to divide the time on each task. Yeah, this is equation number 2, and if you are following up, you may know that what equation numbers we have gave previously, so you can adjust the number accordingly. So what this equation tells us, this relation ensures that psi naught and psi 2 are orthogonal to each other, whereas psi 1 and psi 2 are always orthogonal in all conditions. Okay, so but the condition was needed for psi 2 and psi naught because they were both even, and that is this condition. We'll insert them at the end, but we needed to evaluate this condition. Now let's find out the normalization constant, because that's the next thing that we need to calculate. Orthogonality condition has been evaluated. This is the orthogonality condition. Orthogonality condition for psi 2. All right, now let's find out the normalization constant next. What a decoration. And we know the normalization condition. We know everything. It's the self product, since it's the second excited state, so self product of second excited state trial wave function should be equals to 1. This is the normalization condition, and we know that what psi 2 is, so let's insert it right here. It's minus infinity to infinity. The scalar product is always our whole space, so it's running from minus infinity to plus infinity, or we can say the full domain that on which the wave function is defined. So since the wave functions are defined over whole space from minus infinity to infinity, that is why the limit. Sometimes what happens is that the wave function is only defined in like for example from minus L to L, so these limits will appear in here. Okay, for example, in case of one dimensional box, we can say, and here psi 2 and then psi 2 again dx, because it's one dimensional and 1. Now let's put the values. Psi 2. What for psi 2? It's c beta x squared minus 1 e to the power minus alpha x squared. And psi 2 is again this, so we'll make the square of all this quantity. And in exponential, what happens is the power is added, so it's 2 being multiplied with the power. Okay, and dx, that should be equals to 1. Let's take c squared outside of this integral because that is constant, and we need to solve this integration, and you can see in all the books. Yes, we can see here. Now the next step is to open up this square. It is beta x square minus 1 whole square, so we can open it, and we know the formula, which is a plus b whole square. It's a minus, okay, a minus b whole square equals a square plus b square minus 2ab. So it's beta x square as A and 1 as B. Okay, let's do that now. C square minus infinity to plus infinity. We'll open up the square. It would be a square, which is A is beta x square, so A square plus B square minus 2A and B. Okay, and this whole quantity being multiplied by this exponential factor equals to 1. C squared, now let's simplify it. It's beta square x4 plus 1 minus it's 2 beta x square e to the power minus 2 alpha x square dx. And if you have guessed it, then you must have guessed it right. So what we have to do next is to separate this integral and this exponential factor with each of these three values, and we'll do the separate integration of all of these values. So integration, I'm writing this term first, beta square x4, then this exponential factor with differential dx. Okay, next is plus 1, so plus integral, then this exponential factor multiplies with 1, so the same factor comes back. Then we have this minus sign, and we'll have this integration 2 beta x square e to the power minus 2 alpha x square dx, bracket closes, and it's equals to 1. Okay, so next c square, what we have to do is to take all of these constants outside of this integrations, and we'll see what integral we are left with and what we need to get for them. So it's beta square outside minus infinity to plus infinity x to the power 4 e to the power minus 2 alpha x square dx, then plus we have none of the constant in here, so it's good to go. 2 beta outside, and it's x square e to the power minus 2 alpha x square dx equals to 1. Okay, what we have to do in here is to find out the values for these three integrals. Okay, the same we did for the orthogonality condition, we'll be doing it here as well. So we'll write that we know that we have this rule minus infinity to plus infinity x to the power 2n e to the power minus, I'm gonna use gamma this time. Okay, I have learned from my previous experience, that is equals to pi by gamma 1 dot 3 dot 5 dot 7 dot, the last digit is 2n minus 1 divided by 2 gamma power n. Okay, let's evaluate all these integrals based on this general rule, and we can see clearly in here that let's make the comparisons. And firstly, I'm gonna do it for this one, which doesn't contain any x term, which means that x to the power 0, x to the power 0 is 1 and 1 is everywhere. So it's really simple. We can see that n equals to 0 in here. And what is gamma? We can see anything that is with x square, so it's 2 alpha, gamma is 2 alpha actually. And since n is 0, all of the terms that contains n will be eradicated and will not appear. So this term and this whole term, this whole thing will not be there, only pi by gamma. So we have minus infinity to infinity x to the power 0 e to the power minus gamma. What is gamma? 2 alpha x square dx, that is equals to pi by gamma simply, which is gamma is 2 alpha here. Okay, so its integration is simply this: when there is no n, when n is 0, this whole term becomes 1. Okay, so this was the first integral. Second, we'll do it for n equals to 1 here. You can see it's x to the power 2 and it's x to the power 2n. So if you compare the powers, 2n equals to n should be 1, so that it is similar to this integral. When we'll put n equals to 1 here, it's 2 into 2 into 1 and it's 2 in the power, so it becomes similar to this case. So here we'll have 2n equals to 2 to cancel, and it's n equals to 1. So n equals to 1 is here, and gamma is again 2 alpha. You can compare that, it's 2 alpha. So we can see here x to the power 2 e to the power minus, what's gamma? It's 2 alpha. Wherever there is gamma, put 2 alpha. Pi by 2 alpha instead of gamma. Okay, now here n is involved. We need to see what will happen. 2 into gamma. Gamma is 2 alpha. And 2 2s are 4. Whole power n. N is 1, which doesn't matter. So, and here in the numerator, this term tells you the last term to multiply, and we'll keep on multiplying these odd terms until this last term is reached. We need to determine this last term for each of the cases, and we have 2n minus 1. N is 1 here, so okay, and 2 into 1 is 2, 2 minus 1, which is 1. So the last digit to multiply is 1, which was also the first digit. So it's only 1 in here. We have pi by 2 alpha dot 1 over 2 to the 4 alpha. So this is the value when n is 1. So it's this under root pi by 2 alpha 1 over 4 alpha. Now let's do it for this one, in which we have x to the power 4. So we'll put 4 to be equals to 2n, because it's 2n in our general formula. We'll put these two powers together, we'll equate them. So it's 2 1s are 2 and 2 2s are, so it's n equals to 2. Gamma is again same, you can see it's 2 alpha, and we'll find 2n minus 1, which is 2 into 2 minus 1, it's n equals to 2 this time. 2 2s are 4 minus 1, and 4 minus 1 is 3. So the last digit to multiply is 3. So starting from initial ones, we'll stop at 3. So it's 1.3 only. So we'll get pi by 2 alpha. This is same, 1.3, 2 into 2 alpha, whole power will become 2. It's just that case in this case. It's pi by 2 alpha, 3 by 2 to the 4 alpha whole square, which is actually pi by 2 alpha 3 by 16 alpha square. For 4 is a 16. So that's the expression. Okay, let's put them right back into equation number 3, and I'm gonna put them and we'll get back to you people. Here we go. We can see here I have inserted all of these values, and this is for x4, this is for x0, this is for x1, and they were already there. So let's simplify them. We can take, what we can do here is to take pi by 2 alpha common. I'm taking it common, so it's beta square, 3 beta square by 16 alpha square. Okay, I have took this thing common, so it's not there anymore, plus it's 1 left, minus 2 beta by 4 alpha equals to 1. Now let's take these things into the other side, because we want c, and c is the normalization constant if you don't remember it anymore. So let's take this thing. This is power, whole power 1 by 2, you know, it's under root. So taking it to the other side means it will become 2 alpha by pi whole power 1 by 2. Okay, it will be inverted into the other side, and this is being multiplied in here. It will be divided in here into the other side, or you can say this will become negative power. It's positive power in here, into the other side it will become negative power. It's similar to saying that it's being divided into the other side. Okay, so that is c squared, and what is c? We'll take power 1 by 2 on both sides, so it's 2 alpha by pi power 1 by 4. The power will be doubled in denominator. And here we'll have minus 1 by 2. Okay, so here it's C, this is C. You can see we have got it really quick, and all we have to do is to insert that integration that is frequently appearing again and again, the same one. Okay, oh, we can simplify this one. This is 2 ones are and 2 twos are, so it's beta by 2 alpha minus 1 by 2, and let me write it again. This is the normalization condition or normalization constant, we can call it as 4, and this is the normalization constant for psi 2. Okay, now let's calculate the second excited state energy, the main character of our movie. Let's calculate the energy for the second excited state. Now, as we have seen, this is the trial wave function. Now, the expectation value for the second excited state is the expectation value for energy of the second excited state is given by, all right, so this is the expression that shows expectation value, and it would be a function of alpha and beta, the adjustable parameters, because it will depend and is sensitive to the value for the adjustable parameters that we are going to select, and the variational principle will help us to predict the best possible alpha and beta that brings E2 closer to the original or the exact value for the energy of the second excited state. If you know, then you know that what I'm talking about, since we know that the variational principle or method is an approximation method, and it helps us to predict the best possible energy values and wave function values for the state that we are considering under the trial wave function that we have considered. So the best trial wave function, it means the best solution that you are gonna get. Okay, so this is the expectation value. Later on, we'll just continue with E2 and these angular brackets for simplification. So that is equals to expectation value for the wave functions which are orthogonal and normalized. So since it's expectation value for the second excited state, that is why we'll have psi 2 in here in bra vector. That's the bra vector. And then we'll have the operator which gives the energy values, which is Hamiltonian operator, and it will be applied on the ket vector, which is psi 2 again. Okay, so this is a scalar product of psi 2 and the operator being applied on psi 2. Okay, so that is how we are gonna get the expectation value of energy. And here H bar is the Hamiltonian for the 1D harmonic oscillator, and it's same in all the cases that we have considered before, like in ground state, in first excited state, and it will remain the same for all the states because the operator remains the same, yet the values for the wave functions keeps on changing. So let us call it as 1. Okay, and H bar here, H is the Hamiltonian operator, and it is given by, for 1D harmonic oscillator, H bar equals minus h cut square by 2m d square by dx square. Since it's a 1D case, normally what happens is that it takes following form in 3D. All right, so since we have 1D case, so we can write it as like that. Okay, in the differential, in the differentiation with respect to, this is actually the Hamiltonian operator. This is kinetic energy term, this is the potential energy term. So we have this kinetic energy term plus the potential energy term, which is 1 over 2 m omega square x square, and we can let here for simplification, because we want simplification, as the calculation later on will become so lengthy, and this substitution will help us to narrow down some of the repeating constants that continue to repeat and repeat. So we can simply put them equals to some constants, and we'll later on at the end of the video we'll put them right back into the equation. Here we are just doing it for simplification. Let's put these values right back into Hamiltonian operators. So h has become a1 d square by dx square. I have also taken negative as common, plus a2 x square. So this is the operator. Finally, let's put this operator into this expression. Okay, so put in 1. There are so many calculations that we do using the Cat-Brown notation and using the uh, algebra. It's so easy way to even solve all of the problems utilizing this Cat-Brown notation. There is all algebra related to that, and I'll be talking about it later on in future videos, because now I'm doing all of the requested videos and these calculations are really lengthy. I must tell you, as you can see, that this is the third day and I was ill for the past week, and I was suffering from some cold and fever, and still I have that impact in my that I can't breathe easily. So let's put it into here. So E2, that is equals to psi 2. I'm gonna put this value in here, a1 d square by dx square. This is the value of h operator, so a2 x square. So this is the operator. I'm using the brackets because there are two quantities being added. So this sign, okay, this sign, because this is get and this is bra. Okay, this is bra, this is get vector and this is bra vector. And in previous video, in first excited state, I mistakenly said that this is the cat vector and this is bra vector. That's not correct. I just mistakenly did that, but it was not relevant and it didn't bring any difference to the solution. But you should know that what is cat and what is bra. So the cat vector is always represented like that, okay, while the bra vector is represented in a converse way, like we'll have angular brackets first, then psi, and this like that. Okay, so in bra vector we always take conjugate. In cat vector the vector remains the same. Okay, so in bra vector we have psi star. However, let's get back to our solution. So here we have psi 2 again. Now what we can do in here in cats, this is also a thing that we have psi 2 here, and this cat is common to this term and this term as well. It's just like if we have 2 plus 3 into psi, so we can write it as 2 psi plus 3 psi. It means that both of these quantities are being multiplied by psi. So here the same thing is happening, that this both of these quantities are being multiplied by psi 2 as well as this psi 2 in the left side. So what we can do here, we'll write psi 1 d square by dx square, then psi 2 with this term, then this psi 2, and this one term a2x square with this psi 2 again. Okay, what we have did is that we have separated both of these values with their own cat bras in two separate quantities separated by a plus sign, because there was a plus sign in between them. So that was a easy thing that we do when we have two things being added and some other quantities being multiplied. So from left and from right we have wrote both of these quantities with this and this separately. That is what we have did, and it will help us later on. You will see a1 is a constant. We can take it outside of this Cat-Brown notation. So psi 2 d square by dx square, then psi 2 this, plus a2 psi 2 x square psi 2. This is E2 so far. Let's call it as equation number 2. Okay, now what we are going to do is to calculate this thing separately and this thing separately, and at the end we'll put both of these values right back into this. We'll add them up and we'll see the result. Okay, so as we have seen that a1 and a2 are already taken common, so they will not be repeated again, and that's a good thing. So let's calculate this thing first, because that's easy, whereas this one will will require us to calculate double derivatives. So this one thing will be lengthy while this one will happen quickly. So that is why I'm doing this first. So psi 2 x square psi 2. Okay, you should be familiar with these mathematics and these notations because they are really common in quantum mechanics, and sometimes what we do is to avoid usage of such terms while they are not that difficult, and it's just that we haven't used them before, so that is why we tend to avoid them. Let's convert it into integral that will happen over whole space. Okay, sometimes what happens is that they write it like that, volume integral. That's fine because that's the same thing. It means the volume integral integral over whole space. So we'll have the bra vector first, psi 2, then we have x square. This is operator actually, and that's the thing with that's the thing with the position operators, that when they apply on the psi function, the same value comes back. There is no difference. So that is why I have written it like that, but it's totally up to you. If you write it like that, I'll do it for you. Okay, you can write it like that as well, so it's totally fine. So here it is, and when x square is applied on psi 2, we'll get x square back. So you can see that when we apply the position operator on wave functions, there is no change, while in case of these differential operators, there is a change that occurs and we get a different value. And we have this situation right now. Now let's put the value of psi 2 right here and solve this integration. What's psi 2? Psi 2 is c beta x square minus 1 e to the power minus alpha x square. Then we have x square that is already present. This x square and this x square is same. If you are wondering that I'm writing it like that and the other one like that, they are different. No, they are not different. Let's write them the same way we wrote the other one. So we have psi 2 again. So psi 2 is again beta x square minus 1 e to the power minus alpha x square dx. Okay, and this c and c becomes c squared minus infinity to plus infinity. Let's bring x squared at the start, and we have e to the power minus alpha x square, and this is e to the power minus alpha x square. Again, bases are same, so powers will be added, and we have e to the power minus alpha x squared. And you are now experienced individual because you have successfully calculated the orthogonality condition and normalization condition, and I expect some experienceness from you people. Okay, so pardon me for not mentioning some of the details right now, because you have done it before, so you are grown up now. So it's x square e to the power minus 2 alpha x square. I don't want to spoon feed you. It's squared, whole squared. Okay, and yes, so we'll find out the whole square of it. Okay, but we'll open up the square, we'll simplify the integrals, we'll separate them, and then after that we'll find out the integration values. So using the same formula that we have used before, so it's beta square x4 as a square plus b square minus 2ab. So that is it. Then we have this c squared thing. Now we'll multiply this with this and this, so there will be three integrals. I'm taking c squared common, so we'll have this integration x squared e to the power minus 2 alpha x squared. First we'll write with beta squared x4 dx, then this plus sign, this integral, this thing will again be written. We have 1, so that doesn't matter, so it will end on dx. Then we have minus sign. I can take 2 beta common, and minus 2 plus infinity, and in this integration we'll have this term and x square. So this is x square and this is x square. It will make x4 e to the power minus 2 alpha x square dx, and we'll close the bracket. Okay, I hope you got it. what we have done in here is that we have this whole quantity. There are three numbers in here, 1, 2 and 3, separated by plus and minus sign. So this term is being multiplied by this, this and this, and we have done it. We have just multiplied it with this, and with this. Multiplying by 1 brings back the same quantity, so that is why there is no change in the second quantity. Here we have beta square and minus infinity to plus infinity, and we can see here that x to the power 6 for the first time. So it's x to the power 2 and 4, so the powers will be added. Bases are same, x and x base is same, so powers will be added. 4 plus 2, 6. E to the power minus 2 alpha x square dx plus x square e to the power minus 2 alpha x square dx minus 2 beta minus infinity to plus infinity x to the power 4 minus 2 alpha x square dx. Alright, so this is what we have got so far, and we have three integrals in here, one with power 2, the other with 4, and the other with 6. We have to evaluate their values from that integration formula, and we'll plug that values right back into this equation, and we will get this result. Okay, so then we'll do it for this one. We'll calculate it and we'll plug these values right back into 2. So let me write the formula now. So we have this formula. We know that is not alarming. I'm writing it red color, and me and my lame jokes. X to the power 2n e to the power minus beta. I'm again using beta, na? It's gamma x square. Okay, let me do it again. X 2n e to the power minus gamma x square dx. Okay, that is equals to pi by gamma 1 dot 3 dot 5 dot, the last number is 2 minus 1, divided by 2 gamma whole power n. That is the formula. As you can see, I have remembered this formula. Okay, just for you people, I have remembered this formula. And let's calculate for this one first, maybe then for this, and then for this, and if it's totally up to you, whatever sequence you
E1
wish to follow. So in this case, you can see it's x to the power 6, and we have x to the power 2 n in here. So we can equate 2n equals 6 to find out the value of n for this case. Okay, so it's 2 1s are 2 and 2 3s are n equals 3. So in gamma, we can see if we compare the powers of exponentials, any term that is with x square is gamma. So we have 2 alpha with x square, so 2 alpha is actually the gamma in here. Wherever it's gamma, you'll put 2 alpha. So let's do that, and here we can calculate 2 into 3 minus 1. This is 2 and minus 1. So 2 into 3 is 6 minus 1, which gives 5. So the last digit of this multiplication is 5. Starting from the initial numbers, you will stop when 5 comes. Okay, that is what it means. So it's minus infinity to plus infinity, x to the power 6 e to the power minus 2 alpha. In place of gamma, you'll write 2 alpha x square dx, that is equals to pi by 2 alpha 1 dot 3 dot 5 divided by 2 into 2 alpha, since gamma is 2 alpha, whole power 3. Okay, let's simplify it. Pi by 2 alpha as it is, 5 3s are 15, it's 2 cube and 2 alpha whole cube. We can separate the power on both of these numbers. So let's simplify. 15 divided by 2 cube is 8, 2 cube is again 8, and alpha cube. So 8 into 8 is 64. 15 by 64 x cube. Okay, that is the value of this x to the power 6 one integral. Okay, now let's evaluate its value for this one and this one that we have done multiple times before, and we are doing it again because I don't remember what they were actually. So for 2 1, it's n is equals to 1 for it, and gamma equals to alpha again. 2n minus 1, if you calculate it, it's 1. So this integral is actually pi by 2 alpha and 1 by 4 alpha. Okay, because here the power will be 1. It's 2 2s are 4 into alpha, 4 alpha power 1, which is 4 alpha again, so that is its value. And for this one, there will be only one difference. It will be that we'll have 1.3 in here and we'll have a power of 2 in the denominator. So let me write it here because we have some space. And you know how I'm doing it, because we have done it a ton of times before, so I'm not gonna repeat it. 1.3, it's 4 alpha whole power 2, so it's pi by 2 alpha by 16 alpha squared. Okay, so that these are the values. Let's put them into this. It's c square, this bigger bracket, beta square, then we have this value pi by 2 alpha, 15 by 64 alpha cube. Okay, this is alpha. I have written it x. I'm such a mad person. Then we have x square values, which is pi by 2 alpha, 1 over 4 alpha. Then we have minus 2 beta, pi by 2 alpha, and 3 by 16 alpha square. And this is what we have got so far. And what we can do in here is to take this pi by 2 alpha common from all of these quantities, because it's common and it will be cancelled out at the end. So I'm taking it as common, pi by 2 alpha, and we have beta square 15 by 64 alpha cube plus 1 over 4 alpha minus 2 beta into 3 divided by 16 alpha square, and it's 2 1s are 2, 8s are 16, so it will become beta square 15 beta square by 64 alpha cube plus 1 over 4 alpha minus 3 beta by 8 alpha square. Okay, this is the value that we have got so far. Okay, and I'm gonna multiply a2 with it as well, because we don't want to increase number of steps later on when we'll be adding it here, because here we need to multiply a2 as well. So let me do it here. We know that a2 is simply 1 over 2 m omega square, so I'm multiplying it here. 1 over 2 m omega square c square into under root pi by 2 alpha as well, and we have 15 beta square minus 64 or divided by 64 alpha cube plus 1 over 4 alpha minus 3 beta by 8 alpha square. We can multiply 1 over 2 inside, so it's 15 beta square by 64 2s are 2 4s are 8 and 2 6 are 12, so it's this plus 1 over 4 2s are 8 alpha minus 3 beta 8 2s are 16 alpha square. So this is the value of a2 into psi 2 x square psi 2. Let's call it as equation number A. Okay, now we are gonna calculate the another one quantity, which is this. Okay, we'll multiply a1 at the end. Let's calculate it now, this one. Okay, because we have calculated this one successfully, and that is it. Let's do the other one. That is it. So here we'll have this integral, then we have c beta x square minus 1 e to the power minus alpha x square, and then we have d square by dx square applied on psi 2 c beta x square minus 1 e to the power minus alpha x square dx. Never mistake, never ever mistake to for sometimes what we do directly is to make the square of it and then apply d square by dx. So no, that's not correct. What you have to do is to multiply and apply this one thing, this operator on side 2 first, evaluate it, and then multiply it with another side 2. The order matters a lot when it comes to operators. Okay, so in case of position operators, what happens is there is no difference that comes to the side. As a result, you can write the direct square, but here you can't do that because that will bring a change on the value on the left hand side. So let's calculate this expression first. We'll plug it right back into this equation because writing this whole thing again will make it lengthy. So we'll calculate d square by dx square. I'm not including this one, c. We'll multiply it in here, so it's c square. Since it's a constant, so that doesn't matter. We have actually this thing, no dx, this thing only. So let's find out its derivative. We'll find out its first derivative. This is first term, this is second term. We'll use a product rule inside. So derivative of e to the power minus alpha x square as it is, then derivative of beta x square minus 1 plus then beta x square minus 1 as it is, derivative of exponential term. E to the power minus alpha x square as it is, then we'll find out derivative of this term, which is beta x square minus 1. Derivative of beta x square is 2 beta x, beta as it is, then derivative of x square is 2x, so it's 2 beta x minus derivative of 1 is 0, so it's the same, plus beta x square minus 1. Derivative of e to the power minus alpha x square is e to the power minus alpha x square, dot derivative of its power is minus alpha x square. We'll find out its derivative. Let's continue with the derivative. Here we can see that we have d by dx. It's 2 beta x, so I'm gonna write it here, e to the power minus alpha x square plus beta x squared minus 1 into e to the power minus alpha x square. Then we have this term minus alpha x square, so minus alpha will be taken out outside of the differentiation, and differential will be applied on x square, and derivative of x square is actually 2x, so we got 2x in here. Let's simplify this first and then we'll apply the second derivative. And for that purpose, I'm also taking e to the power minus alpha x square common out of these two quantities because it will simplify the process. Otherwise, we have to take the derivative of this exponential here and here as well. That is not necessary. So we are going to take it common. And we have 2 beta x here plus this beta x square minus 1 into minus 2 alpha x. Okay, this is 2x and alpha, so I wrote it together. Let's multiply it inside of this quantity so that we may get a value, and the more you simplify it, the easier it will become to take derivative of. Okay, so let's multiply minus 2 alpha x with beta x square, so it gives minus 2 alpha beta x square, and this is x cube. Okay, minus minus plus, then we have 2 alpha x as it is. So it's d by dx of e to the power minus alpha x squared and 2 beta x and plus 2 alpha x minus 2 alpha beta x cube. Okay, here we can simplify it further on. Wherever it's possible to take the constant out and separating the variable part, that will make your whole calculation way easier. So you can see that x is common in here, so I took it common, and it's 2 beta plus 2 alpha, which is constant. So while taking the derivative, it could be taken out and the derivative will be applied on x once. Okay, so that is why I did that, 2 alpha beta x cube. Now let's apply the derivative, the second derivative, this one. on these two quantities. This is the first term and this is the second term. We'll use the product rule again. So this is the first term and this is the second term. So first term as it is, derivative of second term, which is 2 alpha plus 2 beta into x minus 2 alpha beta x cube. Okay, then this whole term as it is, which I'm going to write here, and derivative of exponential term. Writing the operator on the right side is always a good thing, and those things on which the operator is not going to be applied should be written on the left side of the operator. Okay, if you are going to write this thing on the right side, then it will make the reader confused about the idea that whether the operator is being applied on this or not. So that makes it confusing. So always use that rule while writing the operators and other factors in one line, that the operators are written on the right side and all those things which are not under the operation of that operator are written on the left side. So I'm going to write this thing on, I just wrote here that this thing on the left side while the operator on the right side here as well. Okay, so the reason is to ensure the clarity and avoid any confusion. So we can apply the d by dx on this term and then this term, because this is applied on this term and this term as well. This is common. So 2 alpha plus 2 beta are constant, so they'll remain inside, and dx by dx is something that is left. Then 2 alpha beta is common, d by dx on x cube. Okay, so plus, then we have this term that is 2 alpha plus 2 beta into x minus 2 alpha beta x cube. We'll be simplifying them at the end. When we have successfully calculated all of the derivatives, we will be simplifying them, okay, as much as possible. So d by dx of e to the power minus alpha x square, which is again e to the power minus alpha x square into 2 into minus 2 alpha x. Okay, that is its derivative. So I wrote it directly again. E to the power minus alpha x square could be taken common, so that we can, now we have two terms. You can see this term and this term separated by this plus sign. So we are going to take this exponential factor again as common, so that we may not have to write it with each of these terms inside. We'll be simplifying them, okay, since they are being added to each other, and simplification will reduce them into lesser number of quantities than what they are now. So dx by dx is 1, so I'm not gonna write 1 here. It's 2 alpha plus 2 beta finally, and 2 alpha beta again. X cube, derivative of x cube is 3x square. So this is it. Now here we can see that we have minus 2 alpha x. I'm going to write it on the left side, and then we have this whole term. Let's multiply x inside, because now we need to simplify it. So multiply x inside, so it's 2 alpha x plus 2 beta x and minus 2 alpha beta x cube. In next step, what we are going to do is to multiply minus 2 alpha x inside of it, so that we have the simplified form, and we can separate all of these quantities based on their variables and their powers. Okay, we'll separate those quantities which have x to the power 1, then x to the power 2, x to the power 3, 4, 0, whatever. Okay, so we'll separate them, because on inserting them, it's 3 2s are 6. Inside the integral, we can do the integration really easily then. So it's 3 2s are 6, alpha beta and x square. Then we have this minus sign, plus minus minus. Okay, so this is minus 2 alpha x into 2 alpha x. So plus minus minus, 2 2s are 4, alpha square x square. Then this, where this quantity is second one, minus plus minus, 2 2s are 4, alpha beta xx x square. So last minus minus plus, 2 2s are 4, alpha and alpha square, and 1 beta is here, x, and x cube, it's x4 then. Okay, so we can see here that it's minus 6 alpha beta x square and minus 4 alpha beta x square. So they can be added Okay, because they have alpha beta, it's x square, they're similar variables and constants. So 6 and 4 makes 10, so it's, we can write here directly, it's minus 10, it's gonna be minus 10 alpha beta x square. Okay, other than that we have this x square thing and this x square thing. So but their, alpha and beta things are not same, so we can't further add them. But what we can do them is to take x square common out of them, and we'll take these things inside a bracket. You will see how I'm gonna do this, and we can see that it's x to the power 4, it's x to the power 2, and here the x is 0. So there are total of 3 different quantities in terms of variable in their powers. So let me write it, and it will be clear to you people. First we'll write this exponential. Well, so we can write 2 alpha plus 2 beta inside a bracket, okay, because they corresponds to this category. Okay, we can imagine the integrals coming up. Okay, that is why I am just separating the constants. Okay, it will help us to take the constants outside of the integral, and we'll have the variable inside. So this classification and separation of the constants make the later process way easier, and there will be, it's almost done, the problem is almost done. And I'm gonna write, I'm gonna take x squared as common. Okay, so it's x square, I took it common, so we are left with minus 10 minus 10 alpha beta minus 4 alpha square inside. And then we have x to the power 4, I'm writing x to the power 4 first, and then 4 alpha square beta, 4 alpha square beta. Okay, just for us to see that we have 3 different quantities in here. This is totally constant, it's x to the power 4 2, just to have an classification that we have 3 different quantities. It's constant being multiplied by a variable, it will be taken outside of the integral. That is why I did that, and we successfully calculated the 2 derivatives of psi 2. Now it's time to put in in star. I just wrote the expression to be star. Let me see where it is. Here it is actually, and this is star, and we have successfully calculated this expression, and now we are gonna insert that expression right back into this equation, and we can see that this term is already here. We'll take c square outside of the integral, and we'll multiply all those factors with these quantities. We'll simplify and separate all of those integrals, and we'll do the final integration. Then it's almost done, it's almost done. Okay, so let's do that now. We'll put it right back into this expression. So let's do that. We have the psi 2 d square by dx square, and psi 2 and c square will be taken outside already. And then we have beta x square minus 1 e to the power minus alpha x square already. And then we have this e to the power minus alpha x square, another one. So let's write it. And then this whole quantity later, let's write it in here, and minus 10 alpha beta minus 4 alpha squared, and then plus x4 4 alpha squared beta, and the bracket closes, and it's dx in here. Okay, now the next step that we are gonna do is, these bases are same, exponentials, these are the bases are same, both bases are e and e, so powers will be added, and we'll have e to the power minus 2 alpha x square. Okay, it's e to the power minus 2 alpha x square. Now next what we are going to do is to multiply this whole thing, e to the power minus 2 alpha x square, and this whole thing with beta x square. Okay, we'll write the whole integral and all these things with beta x square, and then we'll multiply the minus 1. This whole quantity will multiply it with the minus 1, because we can see beta x square minus 1 is being multiplied with by whole quantity. So we can see, we'll take c square outside, so c square is outside, and we have this bigger bracket. Now first we'll write beta x square, then this whole quantity, because this whole quantity is common to beta x square and minus 1. Okay, so first we'll write it with beta x square, and then negative sign we'll multiply it with 1, and that is what I'm gonna do. So it's e to the power minus 2 alpha x square, and we have this whole quantity now. So 2 alpha plus 2 beta plus x square minus 10 alpha beta minus 4 alpha square. Hopefully we are not making any mistake, because before that I have already filmed that problem, but I did a mistake and my answer was wrong at the end, and I was wondering where I made a mistake, and I made a mistake while finding out the derivative, the point where you see that I changed the page. So the reason is I made a mistake. I missed this minus alpha later on, and the mess happened. So be cautious and be attentive to every detail, because it will make you my mind go crazy when the answer is not right. And yeah, so we wrote it like that. Now we'll write the whole thing, we'll multiply the whole thing with 1. So it's minus, because it's minus in here, then integral. Since it's 1, so we doesn't need to write it specifically, we'll continue with this whole quantity. It's e to the power minus 2 alpha x square, and this whole quantity inside. Okay, dx. So bigger bracket close, because c square is common to all these quantities. So next step is obviously to multiply this quantity with each of these three quantities. Okay, here as well we'll multiply this inside of it, so we'll have three separate integrals. So this whole, along with this integration sign, we will multiply with this, then this, then this. So it will be, first we have beta x square e to the power minus 2 alpha x square, we'll multiply 2 alpha plus 2 beta, and we'll have dx, because this integration is now gonna be separated, that is why. Then plus this term again, because it's common to all three quantities, so it will be written again and again, beta x square e to the power minus 2 alpha x square, then this second quantity, which is x square into minus 10 alpha beta minus 4 alpha square, it's dx, its own dx, then plus this integration sign again, because it's being multiplied inside. I'm just repeating it again and again so that you people are not confused. Okay, so this is successfully multiplied inside. Now it's time for this negative sign with this integration to multiply with these terms inside. Let's do that. So e to the power minus 2 alpha x square, then we have into 2 alpha plus 2 beta dx. Okay, then minus sign, because it's minus and plus minus. This integration first, e to the power minus 2 alpha x square, then we have x square into minus 10 alpha beta minus 4 alpha square dx, then plus minus minus again, this exponential first, and then x4 4 alpha square beta dx, and the bigger bracket close. Okay, we can see that we have a ton of integrals in here, a total of 6 actually, which will be reduced right now. So we can see the constants will be taken outside. It's beta, and 2 alpha plus 2 beta is constant, so they will be taken outside. And now you can see that the thing we did before is helping us, that the separation of constants from the variable, since now we have this integration inside whose value we already know, so we just need to insert it back into here. It's x square exponential only, then we have this beta, and then this is this this okay, this and it's, yes, this x square, and then x square, it's x4 total minus 2 alpha x square dx. Next we have plus, it's beta, and it's beta, it makes a total of beta square 4 alpha square beta square will be taken outside, and we have x square and x4, which makes x6. Bases are same. X is base in here and it's same. Here the x is base and x is base. Base means the number or the quantity on which the power is. Okay, so the base to the power 4 is something like a. So we can see here the base to the power 4 is x and the base to the power 2 is x. Base is same, so powers will be added. So x power 2 plus 4, which is x6, e to the power minus 2 alpha x square dx. Minus the next quantity in line is this. We can take this constant outside, so it's 2 alpha plus 2 beta integration e to the power minus 2 alpha x square dx. Then we have this one, integral, and we'll take this constant outside, so it's minus 10 alpha beta minus 4 alpha square, and we have this integration inside e to the x square. We'll write x square first, e to the power minus 2 alpha x square dx. Finally, the last integral in here, which is this one, it's 4 alpha square beta, that is constant, so it's gonna be taken inside or outside of the integral x4 e to the power minus 2 alpha x square dx, and the bracket closes. We can see that some of the integrals are repeating. We can see here that it's x to the power 2 integral, okay, and this is x to the power 2 integral as well. So what we can do in here is to write them together. It's just like they are the similar quantities. We can take this integral as common and we'll have these constants being added, just like taking something common. And we have this x to the power 4 integral in this one, okay, and they are only one like them, so we don't need to do them for this for them for this. So let's do that in next step, because it will make the situation way easier for us to deal with. It's beta 2 alpha plus 2 beta, okay, and I'm not writing this integral right now because we are taking it common, so I'm gonna write this thing next. We'll write only constants, so it's minus with minus 10 alpha beta minus 4 alpha square. We'll use this, and I'm using curly brackets, okay, so we'll have this integration outside. As you can see, if you multiply this integration inside, you will get the similar thing, okay. So next what I'm gonna do is this x to the power 4 integral, so its constants are this here and this one here. So let's write the constants together. So it's plus I'm gonna continue here, beta into minus 10 alpha beta minus 4 alpha square, bracket close. Then we'll continue with its constant, which is minus 4 alpha square beta. The way they are written, write them the same way, just don't write the integrations. Write the integration outside of the curly brackets. So it's minus infinity to plus infinity x to the power 4 e to the power minus 2 alpha x square dx. Then these two integrations will be written the same way as they are written here, because there is nothing common here. So it's 4 alpha square beta square minus infinity to plus infinity x to the power 6 e to the power minus 2 alpha x square dx minus 2 alpha plus 2 beta minus plus infinity e to the power minus 2 alpha x square dx, and the bigger bracket closes. Now we know what is the integration of this quantity, this quantity, this quantity, and this quantity as well as calculated before. So let me mention them again. We can see the integration of x to the power 6 integral is under root pi by 2 alpha 15 by 64 alpha cube, okay. Then x to the power 2 integral is pi by 2 alpha under root 1 over 4 alpha. Then this is the integration of x to the power 4 integral under root pi by 2 alpha 3 by 16 alpha square, and for the integral which doesn't contain x, its integration is simply under root pi by 2 alpha, because n is not there, so this quantity will not be a part of it. Okay, a part of its solution. It's not gonna be a part of its solution because n is not there. So yes, let's put all of these values in here, and meanwhile what we will be doing is simplifying these constants as well. Okay, so we'll multiply beta inside, and we'll remove all of these brackets and we'll simplify them inside these curly brackets. So it's 2 alpha and beta, because beta is being multiplied inside, so plus 2 beta square. We'll multiply this negative sign inside, so negative becomes positive, minus minus plus, and it's 10 alpha beta minus minus plus 4 alpha square. Okay, curly bracket closes, and then we have this x to the power 2 integrals, so its value is this. So let's put pi by 2 alpha 1 over 4 alpha, then this plus sign, curly bracket starts, we have this term, multiply beta inside, and we'll simplify. So multiply beta inside, it's minus 10 alpha beta square minus 4 alpha square beta minus 4 alpha square beta, another one. Curly bracket closes, then we have x to the power 4 integral, whose integration is this, put here. Pi by 2 alpha 3 by 16 alpha square, then this plus sign because this one is done as well, so this is the next candidate, 4 alpha square beta square x to the power 6 integral, which is pi by 2 alpha 15 by 64 alpha cube. Okay, then it's minus 4 alpha square beta, and oh sorry, I just wrote it. No, it's this. Next it's this, minus 2 alpha plus 2 beta, it's written here actually, and this is the next term, which is whose value is pi by 2 alpha, and I'm gonna close the bigger bracket. Next step is to simplify everything, as we can see here. This is the expression to simplify, okay, just to ensure that we are not confused at all. Okay, sustainability. It's c square, bigger bracket starts, and let's simplify. We can see what could be added. It's 10 plus 2, which makes 12 alpha beta. So 12 alpha beta plus 2 beta square plus 4 alpha square. Okay, and we have that under root pi by 2 alpha. What we can do in here is that we can take under root pi by 2 alpha common from all of these quantities, because each of these quantities has under root pi by 2 alpha. Okay, so we doesn't need to write them again and again, so I'm gonna write it here, pi by 2 alpha. Okay, so we don't need to write pi by 2 alpha from each of these quantities. Okay, and we can see that this quantity is written here, we simplified it, and then we have divided by 4 alpha outside of it, so 4 alpha is being divided by each of these quantities, so I'm gonna divide it here with each of these quantities just to reduce the steps. Okay, then we have plus sign, and then we have this quantity minus 10 alpha beta square minus 4 alpha square beta and minus 4 alpha square beta, alpha square beta minus 4 alpha square beta, they can be added. So we have minus 10 alpha beta square, okay, and minus 4 alpha square beta and minus 4 alpha square beta, they could be added. 4 and 4 makes 8 so it's 8 alpha square beta. Then we have 3 by 16 alpha square multiplied outside, so we'll multiply it inside later on. Then we can see that we have this quantity in here, it's alpha square and it's alpha cube, so alpha square cube, so one alpha is left Behind is 4 ones are 4 and 4 16s are 64. So it's 16 in the denominator. So we have 15 beta square plus sign 15 beta square in the numerator, that is left 15 beta square divided by 16 alpha. Then minus sign, we have 2 alpha 2 beta, so minus will be multiplied inside, and it's minus 2 alpha minus 2 beta. Let's simplify again. So we have pi by 2 alpha c square, and this alpha and alpha cancels out, and we have 4 ones are 4 and 4 threes are 12, so 3 beta is left, plus 2 ones are and 2 twos are, so beta square by 2 alpha. For cancellation we'll use that red pencil, so it's 2 twos are, so we beta square by 2 alpha. Okay, then 4 and 4 cancels out, and 1 alpha is left because it's alpha square and this alpha, so we'll have plus alpha here. Okay, then don't need to use any other bracket because it's already done. Let's multiply 3 by 16 alpha square inside, so it's minus 10 plus minus minus, that is why we wrote minus, eradicating any brackets because don't need to do them anymore. 3 by 16 alpha squared minus this one minus 8 alpha square beta multiplied by 3 by 16 alpha square, plus this is already simplified, so it's 16 beta squared by 16 alpha minus 2 alpha minus 2 beta, c square under root pi by 2 alpha. Let's simplify again. It's 3 beta and it's minus 2 beta plus 3 beta minus 2 beta, it means plus beta. This is plus alpha, this is minus 2 alpha, which means minus alpha. Okay, then we have this plus beta square plus by 2 alpha, and we have this 15 beta square by 16 alpha. This has beta square by alpha, this has beta square by alpha as well. That is why we are going to write them together because they are similar. Then we have these ones, let's simplify them. So it's 2 5s are 10, 2 8s are 16. So it's alpha, one of the alpha goes out, and it's 5 3s are 15 beta square by 8 alpha, beta square by alpha again here. Next we can see it's 4 2s are 18 and 4 4s are and 2 1s are 2 and 2 2s are, so it's 2 in the denominator, 2 here. Okay, alpha square cancels out, and we have what we are left with is 3 beta by 2, 3 by 2 beta actually. Okay, yes, c square. Let's simplify, it's almost done. We have this beta and we have 3 by, oh, it's what sign it has, it's negative sign in here, sorry, I didn't write it here. So it's beta and this one has beta as well, so they could be simplified, beta minus 3 by 2 beta minus alpha again as it is. Then we can take LCM. What we can do is take beta square by alpha as common, and we will have 1 by 2 plus 15 by 16 minus 15 by 8 inside. Okay, so 2 is LCM, 2 beta minus 3 beta in here. Okay, we took the LCM simply, and plus beta square by alpha. LCM is, we have 16 8 and 2, LCM will be 16, the reason being 8 and 2 and it's 16. We can do that in rough work. You can confirm the LCM of 8 2 and 16. 8 ones are 8, 8 twos are 2 ones are 2 ones are, so 8 twos are 16, so 16 is LCM. 2 is table 116 is 8 plus 15 minus 15 into 2, which is 30. okay, because 15 is in the numerator, so 15 into 2, which I hope you know how to take LCMs, and c square pi by 2 alpha, 2 beta minus 3 beta, that gives minus beta, okay, minus 1 beta, which is minus beta divided by 2 minus alpha plus beta square by alpha. 8 plus 15 makes 23 minus 30 divided by 16. C square by pi by 2 alpha minus beta by 2 minus alpha plus beta square by alpha. So it's minus 7 brackets by 16. It will be multiplied. So c square pi by 2 alpha minus beta by 2 minus alpha minus 17 by 16 beta square by alpha. Okay, now the next major step here is to multiply a1 inside. Okay, we'll simplify it. We'll calculate this quantity after multiplying a1, which was minus h square by 2m. After finding out this value, we'll plug both of those values that we calculated separately right back into this equation. Okay, and the solution is very near. So we have a1 into psi 2 d square by dx square psi 2, that is equals to a1 is minus h square by 2m into this quantity, which is c square under root pi by 2 alpha. Then we have minus beta by 2 minus alpha minus 7 by 16 beta square by alpha. Okay, so we can multiply this negative sign inside, so it's h square by 2m c square pi by 2 alpha. So it's negative sign will be multiplied inside and everything will become positive. So it's beta by 2 plus alpha plus 17 by 6 or 7 by 16 beta square by alpha. That is its value, and we can confirm it from the book as well. You can see here, this is the same result that we get in here. They have just wrote this quantity on the right hand side and this quantity on the left hand side. So we got the similar result for this quantity and this quantity. They tell us that after lengthy but straightforward calculations we obtained. Yes, that was a straightforward calculation but quite lengthy. So we got these results. Let's plug these values right back into equation number 2, which is this. Okay, and this is another result, another expression that we got previously, that is equation number A. You can compare it with this result on the book. They are similar. So let's plug these values, put into 2. Finally we are gonna put it, and after so many efforts, it's c square under root pi by 2 alpha h square by 2m alpha plus beta by 2 plus 7 beta square by 16 alpha. This was this expression, and then plus and this expression, which was the second expression was m plus m omega square c square pi by 2 alpha and 15 by 128 beta square by alpha cube plus 1 over 8 alpha minus 3 beta by 16 alpha square. All right, and we have got this expression. And what we can do in here is to put the value of c square right here. We'll simplify things, and because now we need to put the normalization condition as well as the orthogonality condition into this expression to turn this expression into alpha only. Okay, so let's do that. We can put the value of c square in here, and c square, this is the value of c. Okay, and what was the value of c square? We can see this is the value of c square, while this is in the negative power. So this is the value of c square. Let's put it here. The value of c square is 2 alpha by pi whole power 1 by 2, which means it's under root. Okay, then we have this pi by 2 alpha, already h cut squared by 2m, then alpha plus beta by 2 plus 7 beta squared by 16 alpha, and we have another term in the denominator. It's actually in the denominator, so I'm gonna write it in the denominator. 3 beta square by 16 alpha square plus 1 minus 2 beta by 4 alpha. Okay, it was negative power in the numerator, and since I have written it in the denominator, that is why it's become the positive power whole. Then you have this plus sign, m omega square, and c square is here again, so we are gonna put its value, which is 2 alpha by pi, and pi by 2 alpha, then 15 beta square by 128 alpha cube plus 1 by 8 alpha minus 3 beta by 16 alpha square, and this whole quantity divided by 3 beta square by 16 alpha square plus 1 minus 2 beta by 4 alpha. Okay, let's simplify. This quantity will be cancelled out. This, okay, it's 2 alpha in the numerator, 2 alpha denominator, pi and pi cancels out, and so it's h cut square by 2m, then alpha plus beta by 2 plus 7 beta square by 16 alpha divided by 3 beta square by 16 alpha square plus 1 minus, it's 2 ones are 2 and 2 twos are, so it's actually by beta by 2 alpha, then plus m omega square 15 beta square by 128 alpha cube plus 1 over 8 alpha minus 3 beta by 16 alpha square divided by 3 beta square by 16 alpha square plus 1 minus beta by 2 alpha. Now we need to put the orthogonality condition in here, and it will help us to get into a simpler form, hopefully. There's one more thing that we can do, is to take this thing in the denominator as common, so that we had to write it only once, and after simplification we can easily multiply it inside. So we can write it in negative power as well. 3 beta square by 16 alpha square plus 1 minus beta by 2 alpha whole power minus 1. I took it common from both of these quantities, and also I wrote it in negative power so that I can write in numerator. It's h cut square by 2m alpha plus beta by 2 plus 7 beta square by 16 alpha plus m omega square into 15 beta square by 128 alpha cube plus 1 over 8 alpha minus 3 beta by 16 alpha square. Okay, that is it. So what is orthogonality condition? Here is the orthogonality condition. So we need to insert beta equals m omega by h cut plus 2 alpha everywhere where is it's beta. Okay, so we'll put this value of beta in here. Everywhere where it's beta, we'll put beta equals m omega by h cut plus 2 alpha. That is the value of beta. So let's put it. So it's 3 by 16 alpha square, value of beta, which is this, m omega by h cut plus 2 alpha whole square plus 1 minus 1 over 2 alpha into beta, which is m omega by h cut plus 2 alpha, and it has this bracket that I wrote in this sign so that we can distinguish the bigger bracket. So next we have these whole quantities, so it will require a bit of hectic simplification, but it would be worth doing it. It would be hectic, but that is it what it is. So it's h cut square by 2m. I'm gonna write this one so that we can differentiate. h square by 2m. Then we have this whole quantity inside, so it's alpha plus beta by 2 beta by 2. Beta is actually m omega by h cut, and 2 is divided, so I'm dividing inside of beta as well. Okay, I directly divided it inside so that we don't use any other thing. Beta square, so it's m omega by h cut plus 2 alpha whole square, and this bracket closes inside because h cut square by 2m is being multiplied with all of these terms inside, and then we have plus m omega square. Then this bracket starts, and this is the whole quantity inside. I'm writing 1 over 8 alpha first because it doesn't contain beta and doesn't require any simplification. That is why I'm writing 1 over 8 alpha first, and then these two quantities first, and then we have minus 3 by 16 alpha square into beta, which is m omega by h cut plus 2 alpha, because it was simpler. That is why I wrote it first. And plus 15 by 128 alpha cube and beta square, which is m omega by h cut plus 2 alpha whole square, and it's closed because m omega square is multiplied with all of these quantities, and then this whole bracket is here. Let's simplify its equal sign. First we have this bracket, okay, 3 by 16 alpha square. Let's open up the square inside, and it's m omega square, m square omega square by h cut square. This is a square plus b square. B is 2 alpha, so its square is 4 alpha square, plus 2 into ab, 2 into 2 omega by h cut 2 alpha, so 2 m omega by h cut into 2 alpha. 2 2s are 4, so this square is completely done. Then we have this plus 1 sign. 3 by 16 alpha square is here, square is opened, okay. Then we have this plus 1 sign minus this 2 alpha is being divided by these two quantities, so it's m omega by 2 alpha h cut, then minus plus minus 2 alpha by 2 alpha, and the bracket closes with minus 1 over 8. Then this bracket starts, and it's plus h cut square by 2m. Then this bracket starts. We have alpha plus alpha is not gonna be solved, so that is why don't need to do that. So it's m omega by 2 h cut plus 2 into cancels out, and it's alpha plus 7 by 16 alpha, and it's another square, same result as this one because this is the same thing, m square omega square by h cut square plus 4 alpha square, and it's 2 2s are 4, or plus 4 m omega by h cut alpha, okay. So that is the square, and this bracket closes, okay, as you can see wherever it is, so keep track of that. Then plus m omega square, bracket starts, 1 over 8 alpha. In next step we have this minus 3 by 16 alpha square being multiplied by these two quantities, so let's multiply them inside by 316 alpha square m omega by h cut minus 3 2s are 6 alpha by 16 alpha square plus 15 by 128 alpha cube, and it's square m square omega square by h cut square plus 4 alpha square plus 4 m omega by h cut alpha, okay. And we have two brackets closing here. One is this and this, and the other is this, which is, okay, you can see it, okay. This is starting and this is ending, this is starting and this is ending circular bracket as well. Let's simplify. here we need to multiply 3 by 16 alpha square inside. So it's 3 m square omega square by 16 alpha square h cut square. Okay, you can see it. Then plus 4 3 is a 12 alpha square by 16 alpha square. But this one is 2 2 is a 4, 4 3 is a 12, 12 m omega alpha by h cut, and this is 16 alpha square h cut. Then plus 1 minus m omega by 2 alpha h cut. 2 alpha cancels out, is minus 1, and we have this as whole power minus 1. Then this starts h cut square by 2m. This starts, it's alpha plus okay, yeah, it's m omega by 2 h cut plus, okay, this is alpha and this is alpha, it made it 2 alpha, so we can write it here 2 alpha. Okay, I cancelled it and it's 2 alpha, and we can multiply this quantity inside. It's 7 m square omega square by 16 alpha h cut square plus, it's 7 this, you can see this is 4 and this is 16, so they will cancel out. It's 4 ones are and 4 fours are, so it's 4 in the denominator, that is less 7 by 4 alpha, and it's alpha square in the numerator will cancel out in the next step. Plus we can see this is 4, it cancels this 16 and makes it 4, so it's 7 by 4. Actually, at least this simplification is done beforehand by h cut, m omega alpha by h cut as it is. Then we are closing this bracket. This bracket closes. Okay, so this is the starting and this is the end of this bracket. Then plus m omega square, this bigger bracket again starts, and we have 1 over 8 alpha. Hopefully we will have some things that will be cancelled out, something that would be cancelled out, and something that will add up to, you know, little results. So it's minus 3 m omega by 16 alpha square h cut, then minus this quantity, we can see it's 2 3s are 6 and 2 8s are, and 1 alpha cancels out, so it's 3 by 8 alpha, plus we have to multiply it inside, so it's 15 m square omega square by 128 alpha cube h cut square plus 15 alpha square by 128 alpha cube plus 15 multiply 4 m omega alpha by 128 alpha cube h cut. Okay, and this bracket closes and the bigger bracket closes. Now we only need to do the simplifications. Okay, as you can see that there are a ton of things that are going to be solved. This plus 1 and minus 1 cancels out. What a relief. And here nothing cancels out actually. Here you can see, so we'll write it as it is. 3 m square omega square by 16 alpha square h cut square. This quantity remains like that. Okay, it will be whole power negative 1 at the end as well. Okay, so just don't assume that it will be cancelled out at the end. No, not gonna happen. It will remain here. So plus this alpha square cancels out, and it's 4 3s are and 4 4s are, it's plus 3 by 4, and plus we can see this alpha and one of the alpha cancels out, and it's again 3 by 4. Okay, it's 3 and it's 4 in here. 3 by 4 m omega by alpha, and it's m omega by alpha h cut here as well. It's m omega by alpha h cut. Okay, I have to do it in two separate steps. I was just thinking that maybe I can skip one more step, but yes, we have to do it. We can see that both of them has m omega by 2. Both of them have m omega by alpha h cut, m omega by alpha h cut, so they can be added. And they will add up, okay, to give this factor. You can see here they will make up this factor. Okay, 3 by 4 is already there. This quantity is already formed. Only this one is left, which will be formed in the next step. And you can see there will be 5 different steps. Oh, sorry, five different quantities in here as well. When we'll solve and simplify this part, we'll get 5 terms. Okay, and here we'll have 3 terms. We can see already it's 1, 2, and this one will be the third value. So we are almost done. Okay, so I don't know how many of the students will continue to watch this part of the video, because I can tell it's already 2 hours, and I'll salute and totally believe in those students who are doing this problem till this point, because they are as much dedicated, as much persistent and consistent with quantum mechanics as I was, because I can do that, and I'm doing that. I'm making this video from the past week just because I just got ill and I made some mistake and I had to do it again and again and again. So that is how it's going on. So that's the beauty of quantum mechanics and complex mathematics. Complex in terms of it's lengthy and there's no space for errors in it. Let's simplify. H squared by 2m. This starts, and we have m omega by 2h cut. Let's see what cancels out. This is alpha and this alpha cancels out, and it's 7 by 4 alpha. Okay, and here nothing cancels out. M omega by 2h cut, nothing cancels out. Here alpha and alpha cancels out, and we can see that this is m omega by h cut and this is m omega by h cut. So they are similar. We'll write them together. This is, we are gonna write it separate, and 7 by 4 alpha and it's 2 alpha, so we'll write them together because they could be added. So it's square first, 7 by 16 m square omega square by alpha h cut square, then plus we'll have m omega by 2 h cut plus 7 by 4 m omega by h cut, okay, plus 2 alpha plus 7 by 4 alpha, then plus m omega square, and we'll do the same thing here. We'll simplify and we'll put the values together which are similar. So the square one will be written first because there is nothing else that could be that is similar to it. So 3 3 3 3 is something cancels out in here, nothing cancels out in here, so we are gonna write this term as it is here first because it's not gonna be solved. So 15 by 128 m square omega square by alpha cube h cut square. Now let's see next. We have this 1 over 8 alpha and minus 3 over 8 alpha, so I'm gonna write them together, plus 1 over 8 alpha minus 3 over 8 alpha, because they will be added, so they should be written together. And here as well we can see that it's alpha square and alpha cube, so 1 alpha will be left behind. It's 15 over plus 15 over 128 alpha. Okay, now these two quantities are left and they will be similar, I hope. So we can see here one of the alpha cancels and it's alpha square in the denominator, it's 4, and we have 128 in the denominator. So 128 is actually 64 times 2. So 4 divided by 64 multiplied by 2. 2 ones are 2 twos are 2 ones are 2 threes are and 2 twos are 32. 32 they for ones are and for 32s are. So let's write them together as well. First this one, minus 3 by 16 alpha square. It's m omega by h cut and m omega by h cut, and it's plus 15 m omega divided by 32 alpha 32 alpha square h cut. Okay, so yeah, and this bracket closes in here, and then this bigger bracket closes. Okay, now we need to simplify them further on, and we'll reach the end. We actually missed one number, as we can see that this is 15 by 128 alpha cube. Okay, that is being multiplied by m square m omega square by h cut square. So here we can see that where we wrote it is here. Okay, you can see that 15 multiplied by this quantity is written here. When this is multiplied by 4 alpha square, we can see that it's 15 by 128 alpha square and alpha cube in the denominator, but it's another 4 that I missed writing here. Rest of everything is correct. I included it in here, but I just missed in here. So with 15 multiplied by 4 by 128 alpha, it will be 15 into 4, which is here. Okay, so I'll be taking it later on, we'll solve it, but just I mention it here so that you can correct it, and we'll proceed with this value. Okay, because I did it you can see, and I made a mistake, and again I had to see each and every step to see what I missed. So this is 4 that I missed. So yeah, rest of everything is correct. So we'll be continuing here. From this step onwards, we'll be taking LCMs and we'll simplify. Okay, so let's continue this. Alright, so this is 3m square omega square by 16 alpha square h cut square plus 3 by 4, which is already solved, and we can see here that it's m omega by alpha h cut, and the only numeric numbers are 3 by 4 and it's minus 1 by 2 here. So let's add 3 by 4 and minus 1 by 2 and see what the result is, so we can write it directly, and we may not need to do write it all the times, and we can do it on rough work. So it's 4 3 minus 2 and it's 1 by 4, so it's plus m omega by 4 alpha h cut, which is what we needed as well, because it's also mentioned in the book. So this is actually achieved. Now we need to simplify these terms. So for that purpose, this bracket starts, and we have h square by 2m into 7 by 16m square omega square by alpha h square, because there is none other term that has this thing, so it will not be simplified. Then plus sign. Then we have this thing m omega by h cut, m omega by h cut. So numeric numbers are 1 by 2 plus 7 by 4. So let's do that and see what the result is. 1 by 2 plus 7 by 4. LCM is 4. 2 plus 7, 9 by 4. So it's 9 by 4 plus sign 9 by 4 m omega by h cut plus 7 by 4 and 2 with alpha as. So 2 plus 7 by 4. 4 is LCM. 4 2s are 8 plus 7, which is 15 by 4. Okay, so it's 15 by 4 in here. Then plus m omega square. Here bracket starts. This square term will appear the same way. 15 by 128 m square omega square by alpha cube h cut square, plus then we have this term, the problematic term. So let's do that. It's 1 over alpha every time. So 1 over 8 minus 3 by 8, 15 into 4 by 128. So 1 by 8 minus 3 by 8 plus 15 into 4 is 15 into 4 divided by 128. And 128 is actually 8 multiplied by 2. So the L is 128. Okay, so with positive sign, 28 divided by 128. So it's 28 divided by 128, and alpha is there. And other than that, what we have is m omega by h cut, and we have numeric numbers m omega by h cut alpha square. 3 by 16 and 15 by 32. So let's do that as well. It's minus 3 by 16 plus 15 by 32. So the LCM is 32. 16 2s are 32. So 2 2 3 is 6 minus plus 15, which is 9 by 32. So we got plus 9 by 32 m omega by alpha square h cut. Okay, brackets close and bigger bracket closes. Now the next step is actually to multiply h square by 2m inside and m omega square inside. Okay, doing so we'll simplify and we'll add similar terms and we'll get the result. Okay, let's do that because I wanna complete it today at all costs. 3 by 4 plus m omega by 4 alpha h cut. My battery is low. Actually my phone battery is low, not my. So this is h square. This, let's multiply h square by 2m inside. So what's gonna happen is that h square cancels out, and yeah, this is the only thing that will happen, and this m and one of the m cancels out, so we have 7 m omega square by 16 to the 32. This m goes out, alpha h square is gone. Now we'll multiply h square by 2m by this quantity. 1 m cancels out, and we have 1 h cut in the numerator only because this is cancels out, and we have 9 by 4 2s are 8, 1 h cut omega only. Okay, then plus this is 15 by 4 alpha, so it simply gets multiplied 15 h cut square by 4 2s are 8 m in the denominator because nothing cancels out. Well, next is plus m omega square multiplies inside, so it's 15 by 128. There is no numeric changes because there is no number in here, so nothing cancels out, only m omega square simplifies. It's m and this is m square, it becomes m cube omega square, so omega 4 divided by alpha cube h cut square plus 28 by 128 alpha m omega square just being another thing 32 alpha square h cut, it will become m square and it will become m cube. So let's simplify it, the things that are simplifying. Okay, so we have the term which have omega 4, so we'll write it as it is because there is none other term that had omega 4, so it will not simplify. It's the final one, m omega by m4 omega 4, sorry. Then omega cube term, here it is, it's plus 9 by 32 m square omega cube by alpha square h cut. That's final as well because it's not gonna be solved further on. Then we have this term and this term, they will be simplified. Okay, as we can see, so it's m omega square by alpha, so it will be added, and let's do that. Okay, sorry, here we can see it's 14 by 4 alpha, so 14 by if we multiplied actually h square by 2m, but we just didn't write the alpha in here, so it's alpha, we write it. So let's add these two terms together. It's 7 by 32 plus 28 by 128. LCM is actually, it's actually, the case is 32 multiplied by 4 is 128. So LCM is 32 multiplied by 4. 32 cancels, 7 4s are 28 plus this whole cancels 28. It's 8 plus 8 is 16, 156 divided by 32 multiplied by 4, and we can cancel out something. You can easily do these cancellations on calculator. You will get 7 by 16. I currently don't have a calculator at the moment because I am at, I don't know, whatever. So it's 7 by 16, then m omega square by alpha, m omega square by alpha. Okay, then we have this term plus 9 by 8 h cut omega. And then we have this lastly the term which is 15 by 8m h square alpha. Finally, we got the terms the way they are supposed to. This is actually the energy term, and we'll apply the variational principle on this expression, and we can see and compare on the book that it's 18 in here. I think that's a printing mistake because I have done it multiple times and I haven't obtained 18 in here, so it might be a mistake in book because the rest of everything is correct. So yeah, so we can do the rest of other things. Now we'll apply the variational principle, and we'll see what result we'll get. So applying the variational principle will give us the value of alpha that we will plug back into this expression, and after simplification we'll get the energy value for the second excited state of 1D harmonic oscillator, and putting the same value of alpha into the wave function, we'll get the wave function for the second excited state of 1D harmonic oscillator. So let's do that.